Okay, where do I want to start?
What do you measure? It's just.
Okay, so I'm going to time myself. I'm only allowed to talk for 25 minutes because when I looked at your classwork, most of you did that. Wait, here it is, right here. Right, so that's kind of cool, right? That when we doubled that over, the area was n times n plus 1, and then you took half, and then we all said, cool, right? But I noticed most of you only got through like one of the toothpick houses problem. Couple groups, now this is what always happens, right? A couple groups whipped through, they were like ready to go on to the sequences. Other groups work much slower. So that's why in teacher language, we call it differentiating instruction. So what that means is that I have to be ready with a harder problem for those groups that whip right through everything, right? Because I could just say, I'll go home early, but those groups need extra challenge. So in teacher language, that's called differentiating instruction. So I'm only giving myself 25 minutes to talk so that you can finish the participation. So first of all, this morning, I posted a couple of things. So I posted the answer key. So after class today, you could check your answers to the toothpick house problem. One of the cool things that I want you to note is like different ways that we could have found the formula, which we talked about a little bit yesterday. And one thing that I want you to know too about writing a formula, we could, some of you wrote that, hang on. You don't have to copy this, but you wrote like something like nth house equals, and then you had something like this. We should write these as equations. Sequences are functions, right? And you've heard the word function before. The simplest way to describe a function is you put something in and you get something out, okay? So what we input is our position. Right, so are we at the first house, the second house, the third house, the fourth house, and then what we output, this was the number of toothpicks, right, or dots. I think one of the problems had dots. Okay, so we should write these as a formula. So I know yesterday I wrote one. Actually, I think it was this one where there was a T, or you could use, because we are looking at sequences, we do end up getting sequences, and this language means like sequence A, the n term. Okay, so where n is which term we're on, right? So we'll talk a little bit more about that, but we should be writing those as equations, and I didn't emphasize that enough on Wednesday. So I want to talk about, I just put a couple things up this morning. So like I said, one of them was the answer key on the toothpick houses, which I hope you finish in class today. Then I put suggested number 2 that you could start working on. So that's not collected. And then I just put up collected, and I put in here, like when we get ready for a test, you're going to be asked someday to write your objectives. Your objectives are a list of things that you want your students to learn. Okay, so I mean, some of these are sort of vague, right? Systematically represent solutions and give detailed answers to solutions, things like that. So we're going to get into problem solving. We're going to talk a little bit more about sequences, which I hope you looked at that homework where you had to and some of them were super easy, right? That homework where some of it was like add 3, like, oh, duh, right? But then we're going to talk about how we could easily write a formula for the nth term in a sequence like that. We're going to start getting into some algebra. We're going to look at some algebra and then like some sets, and that'll become all the material for the first exam, which I think is like the end of the month. Okay, so I am going to make this collected due the 18th. A couple things that I want to talk about with it. Number 1 is like people will look at this and they're like, is there a formula? Is there something like that? Problem number 1 is kind of a bit of a guess and check, right? Or a process of elimination kind of problem. And sometimes I tell students to actually, make the cards. Right, so we have 12 written on one card, 9 on the other, right? And make sure, so if 12 is written on one card, this is the back of 12, right? And then 9 is written on the other card, and you have to find what is written on the back of the other card, okay? And you have to get sums. You have to be able to get these 4 sums, okay? Obviously, the sum of 21 we can get already, right? So then we have to just start looking at, well, what numbers could I put? How am I going to get a 15? How am I going to get a, and like kind of use a process of elimination, okay? Or actually get note cards and, try the different combinations. So people come to me and they're like, isn't there a formula? Because we're so used to there's always a formula that we use, right? So this is just a problem solving kind of process of elimination, a little guess and check. Then this is an exercise in using patterns. The hint that I want to give for number 2, right? Because it asks how many distinct squares can be found in a 5x5 panel. There was a problem with how many triangles can you find on the suggested homework. Suggested number 1, where I said this will help you with one of the collected problems. So I would suggest you look at the triangle problem on suggested number 1 before you tackle this. But what I want to make clear is, and first of all, some people will answer very simply, oh, well, there's 25 squares, right? But those are just the little ones, right? I could look at that and say, I see 1 square. Just happens to be all broken up into pieces, but I see 1 square. Right. So what you have to consider though, so I always put letters in it to kind of help you see this, A, B, C, F, G, H. So I'll like go through and put letters. And if you want to start out that way, that's fine. But like what I want to point out is J, K, L, M, O, like A, B, C, F, G, that's a square. Right, that's its own square, but then BG, CH is a different square, right? As long as it's got some different letters in it, right? And then FGLK is a different square. Okay, don't forget we could do like all different sizes. So you don't want to, because I will see people who will come into my office and they'll have like 2 pages of drawing all these squares. So you don't want to do that. You want to be looking for patterns, okay? So for example, I gave you, come on. Okay, thank you. I gave you, I just gave you the answers, 49 ways to do the coin problem. There's actually a stamp problem on this, which is similar to the coin problem. But if you wrote out every single way you could do the coins, you would have, there are 49 ways. Do you want to write 49 lines? That's a lot of writing. But once, like, if you look at my work, once I noticed a pattern, I was like, oh, well, wait, there's 7 ways to do, there were 5 ways to do it up here with 3 dimes. Then there were 7 ways to do it with 2 dimes. So then I bet you that there's 9 ways to do it with 1 dime and 11 ways to do it with no dime. So I looked for the pattern instead of writing everything out. Okay, so a pattern will develop, but you do need to think in terms of, you could have a 3 by 3 by 3 square. Okay, and then when you find the pattern, you're going to extend it to what do you think is going to happen in a 6 by 6. So I have seen some students draw a 6 by 6 panel, put all the letters in it, and first of all, there's not even enough letters to go into 36 spots and be right. And I'm like, no, right? You don't want to do that. Okay, so we want to make use of patterns. Then there's a toothpick house problem, which we've been doing today. So that one's not usually too bad. Again, these tend to be the harder ones. I would say if anything gives students the most trouble, it's these. Again, we're going to, N is the, which one we're on. Wait, I do think there might have been issues. I'll have to double check it. There might have been issues with this. I'll have to check and make sure the dot right here not showing up. I'm gonna check that because your first, your second, so everything is a function of its position, right? So it's a function of this is N is 1, N is 2, N is 3. Some of these are pretty easy. Some of them you can get quickly, but this is usually where students run into a little bit of trouble. Now, remember, this is not due till Monday the 20th, but the reason I'm giving you 2 weekends in a full week is this is not a due the night before problem set. Okay, this is a, and then another thing that sometimes makes students panic is they say, oh my gosh, are you going to put problems like this on my test? Because this took me like 45 minutes to figure out. That a lot of times problem solving, like that's why it's really hard to legitimately test problem solving, because problem solving is not supposed to be something you can do really fast, right? Problem solving is like, think about it this way, try this way. I know when I get a new math problem I've never seen before, which is kind of exciting for me because I spend most of my life doing math I already know, right? And then once in a while, somebody will give me a new problem, and if I might work on it for a little while, and then like cannot figure it out, and then I'll like be washing the dishes and all of a sudden I'll go, oh wait, maybe I could try that, and like I go back to it, right? So legitimate problem solving can be like a long process. Okay, so give yourself lots of time to do this. We have to talk about inductive and deductive reasoning, and here's like the postage thing, but notice on here I want you to describe how you're doing the problem. Okay, describe the patterns in your table. You get a point for the answer and 2 points for explaining it. So think about, again, thinking systematically. How do you describe the systematic thought process that you went through? Okay, so deductive and inductive reasoning. So that's something I want to talk about because, okay, good. I did this. Ooh, maybe I will make it with only being able to talk for 25 minutes. Remember the first day of class, you don't have to get this out or anything, but remember we were doing this and we said, well, a pattern's going to develop, and some of you notice, oh yeah, you just add the 2 numbers before, and that's how we get from one to the next to the next. And I said, well, how confident are you that that would keep on working? I mean, it might have worked for a little while, right? But how do we really know that that pattern worked? And did we really know? I mean, do we really know without doing it that HI would be 34? I mean, it followed a pattern, but you kind of like guess in a sense, right? When you follow a pattern. And we use this type of reasoning a lot in our lives. Like I remember one time my son had like this skin condition on his face. And now my neighbor told me, I think it's ringworm. That's what my neighbor said. And I brought him to the doctor. The doctor's like, no, he has this and put this cream on it. So it was this really, it got way worse. And it was this very, very bright sunny day, the first bright sunny day of the spring. My son's playing outside, his rash got worse. So I'm like, the sun made it worse. So I'm telling his daycare lady, like, put lots of sunscreen on it. It's, it's making his rash worse. And then his rash kept being worse and worse and worse. And so then finally, so that was like inductive reasoning where I said, I observed something happen. That must be the cause, right? And then I continue to observe it's getting worse. It's getting worse. The worse it gets, the more medicine I put on. I wonder, could the medicine be making it worse? And I turned out I went back to the doctor. The doctor said, yes, it is ringworm. Oops, sorry, I gave you told you the wrong thing. So my neighbor was right. And then she's like, oh yeah, on ringworm, if you put this cream on, yeah, it gets worse. So again, when you like observe something happen and you say, oh, this must be the reason this is happening, right? Or you probably do that like, oh, if I wake up too early, I get a headache, right? And that's again, like I observe something happening, but then some morning you're like, oh, I woke up early, I don't have a headache, or I have a headache, but I didn't wake up early, like things like that we can't always count on. So that type of reasoning, the type of reasoning we use here where we're extending patterns, that is known as inductive reasoning. So there's two types of reasoning, then inductive and deductive reasoning. Okay, so inductive reasoning is when we form a conclusion by observation. For example, middle schoolers will form not middle schoolers, elementary school students will form the conclusion that multiplying makes numbers bigger. When you multiply, you always get an answer that's bigger, but when you divide, you always get an answer that's less. Okay, so that is a conclusion that elementary students will use. So the process of forming conclusions on the basis of patterns. All right, so we used a pattern on that crawling critters. Observations, so making observations of my son's rash, right? I drew my conclusion by observations. Examples. And middle schoolers can come up, or why do I keep saying middle schoolers? Elementary schoolers could come up with infinitely many examples of multiplying two numbers and multiplying two numbers and the answer gets bigger. Right? They come up with countless. So let's say this about inductive reasoning. First of all, it's a cornerstone to scientific discovery. Right, so we would get no new discoveries if somebody didn't say, gee, I noticed that when I mix these two chemicals together, this happens. Right? Or, drug testing. It's all based on experimental data. They have a control group, they have a placebo group, they have a group they give the drug to, and they observe what happens and they draw a conclusion based on observation. Okay. So often when we do this, it leads to an educated guess. Which we call a conjecture. In math, we often call them conjectures. Okay, so I notice that this always happens, therefore I create this conjecture. Right, which is an educated guess. Right? Now, it has its weaknesses. So first of all, I'm in elementary school, okay? So I conclude that every time I multiply, the answer gets bigger, right? The answer is always bigger, and then when I divide, right, I divide 12 by 3, the answer is smaller, right? And so what's the problem with the conclusion that multiplying always makes things bigger? What's the problem?
You multiply by a fraction.
Exactly, right? Because they haven't been doing this yet, where you multiply and the answer gets smaller, okay? So the problem is that conclusions are drawn only from collected evidence. So we haven't tested all cases, okay? So things that we have to consider: can a pattern, quote, break down? Right? So there, the page where you were doing the sequences, there's actually a third page to that where it talks about finding, it shows where you find a pattern, and so you assume the pattern works, and then you get to a point and it doesn't work anymore. Right? And so that's what we really didn't know here, right? I mean, I told you the pattern will work, and so you believed me, and we said this is how many ways, but we really didn't know if that pattern would continue. So will the pattern break down, or will a generalization have an exception? Right? So when we say you multiply, the answer gets bigger, well, that's true an awful lot of the time, except not if you're multiplying by a proper fraction, okay, or a fraction in between 0 and 1. So other things we want to say then about weaknesses is that not all cases, right? Conclusions are drawn only from collected evidence, and not all cases have been tested. Okay, so we can get, you know, here's an exception to my generalization, right? And the same type of thing, like my daughter was learning fractions in school, and she was adding fractions, and she's like, well, Mom, they say to get a least common denominator, but she says, I noticed that you always just multiply the denominators, and that's your least common denominator, right? Well, that's because she hadn't done any fractions like this yet, which would have a least common denominator of 24, not 96. Okay, so she had only been doing, and actually we're going to talk about when, that's sort of a fun lesson. When is the least common denominator just the product versus when is it not? That's a fun lesson. I like that lesson. But anyway, I'm gonna have 5 more minutes. So, okay, keep focused. Knock it off on a tangent. Okay, so anyway, so let's say this about that conclusions are drawn only from collected evidence. Not all cases have been tested. And sometimes you can't test every case. So these things where we're saying like the 100th toothpick house is going to have this many, or the 100th house is going to have this many toothpicks. We are using inductive reasoning because we're assuming that what we noticed on the houses with, you know, the first, second, third, fourth, fifth house, we assume that's going to keep working. We do have some ways in math though, because most of the sequences that you get with the toothpick houses, most of them end up being like the one we were doing the other day, which we kept doing this with the, this was this one, right? Where we kept adding two, adding two, adding two. It was this one. We assume that will, the formula we got will always work. There is a way mathematically, you know, I don't know, your notes are going to get messy because this really doesn't have, this actually doesn't really have anything to do with this. Don't write this down yet. Don't write this down because this really doesn't have anything to do with this. But anyway, one of the things that I'm going to have the groups who finish early work on is that this sequence. And so last night you were doing, if you did it, which I hope you did, you were doing sequences that looked like this. Okay. So for those of you that do finish the classwork early, I'm going to ask you to try to find a formula for the nth term of some of these sequences. Okay? But anyway, a sequence is a function because every term in the sequence, we might get this just listed as a sequence like it was on the homework last night, but everything is a function of its position. Okay, so this row here is the input, and then the value in the sequence is the output. Okay, so a sequence is a function where the terms in the sequence are it's a function of its position. Okay, so those of you that do finish, if you finish your participation early, can work a little bit on that. Okay, so let's see. I have, oh yeah.
For next week, are we allowed to like work together?
Oh, that's a great question. Okay, so for the collected, Joan is allowed to help you. You can come to my office hour. You are allowed to work together, but I should not see work that's a carbon copy of someone. And it's easy to tell when people just copied, like they'll change lines at the same point in their text. Like you trust me, I can tell when people have just carbon copied. Like I can tell a lot of times when people work together, and that's fine. But yeah, that's a great question. I'm glad you asked that. So anyway, let's break down this about deductive reasoning. Right, and you've probably heard the word deduce. Like, well, you should be able to deduce from what I'm saying, right? And that is the process of reaching a conclusion from ideas we accept as true. Right? This does not need to really new discoveries. And so we'll write a little bit more down about this in our notes then Monday. Yep, see, there's my alarm going off telling me to stop talking. So no new discoveries. And like in math, we love this type of thing because in math, we do stuff like A proves B. Well, then B proves C. And then C proves D. And then from D, we conclude E. Okay, so I'll say a little bit more about deductive reasoning next time. So where we left off, and I have to pass back your participation papers for you. So a lot of you were still on that toothpick house. You still need to do number 3 on the toothpick house. Every answer I saw that was correct. And then you had to work on this. So again, as I differentiate instruction, if some of you don't get to this, it's not the end of the world, right? So if your group, if you could at least figure out like this first one, then we could probably say, all right, that, you know, you've done a variation on Gauss's sum, but then those of you that are more advanced, definitely I hope you get through 4. And then if your group does finish everything early, I'll tell you what sequences to work on. So if you want to go back and get into your groups, and I will pass back the papers.
Yeah. Here, Isabella, and then, Sophia. So let's see. Yeah. It looks like you didn't get through number 1. So do you want to? Why don't I? Yes. So yeah. Lots of money. So. If you were to look at number 1, there's a couple of different reasons to look at it. So like it's stuff out here. It's like one. How would that be wrong? Okay, so. Yeah, so there's that. And then like where else? So what we always do is we go from one to the middle. And then one has to be. Yeah, yeah, there you go. Always happens to be 3 times. And then always 2 ones. Then how was that? I'm always. All right, so now what you two try, you go ahead and try yourself. So let me come over here and we're going to be out. Okay, so that's. Okay, we have something to do.
Trying to find out what end.
Yes, we're trying to get this one. We have again.
Yeah.
We have n.
It's so like 2,000 equals 2.
The third, the 4.
That's the next, yes.
You're showing on the answer. Yeah. Read it from ways. Right, so, you know, if it helps you, you can write the top. Yeah. We want to do. Somebody else. This depends. So I'm just. Adding one to the middle. Another one you're on.
Oh, I was just making sure that these were equal.
So there's. Okay. Yes. So like, do you see the end in the middle? Like this other side. So you're saying, I see the end here, and I see the end here. I see the end here, nothing else. I have 3 ends, that's the problem. I want 3 ends, but I always most of the curves, yeah, don't count. But I don't count because well, because if I can answer, if I can take S, I make 3 square to here, never. So how many is that? 2. Or here's another one. This is what I want to do. So I see N in the middle.
N is 4, here's 1. Well, here N is 3. What is always below?
And then it's a possible, like, so
Yes, that's that. And then above it, I get. So this is N, then I guess that's 2. So then below N is this, above N is this, so. Which is 5. So how would we describe
The N was like
time to time?
So like section, so like 1, 2, 3, 4.
In terms of that, like, N is 3, but then above it, you get 2.
I listed that.
N is 4. And above it, we have
3, this represents this. Yes. So this is N.
So how would
This is
you
like
describe it? N. What
blocks.
would you call this piece?
I think that's all we do, so because
Yeah, you
if
can
it
write
were
it.
to just like. But it's not doing like so. But so. 1 zeros.
And that one is the lowest. So like that's square. We could call this. Minus 1. But also and minus 1. Okay, so we could write this. And sometimes people will look at this and say, oh, but that's not the same as the other answer. Like, that's 3 N's minus 2. Yeah, yes, but then we put 1 plus 6. You're welcome. Yeah.
All right, so hang on, groups that are finishing, I'm gonna write some for you on the board.
Oh, yeah.
I think you're.
So it'd be like. Number 8.
Yeah, there's a huge one. It's very easy.
So I want you guys, if you finish, work on finding a term then of some of those sequences from last night.
All right, so it's, has everyone at least moved on to this pretty much?
It's like these,
So actually, I'm gonna end the meeting because you know what you're supposed to be working on. So finishing the toothpick houses handout, and then working on these sums.